Welcome everyone to the Claude Hocott Lectureship in Petroleum Engineering at the Hildebrand Department of Petroleum and Geosystems Engineering. I'm pleased to introduce today our speaker, Dr. Musa Maharramov. That's what I thought it probably says, but.
Yep, that's right.
Okay, sorry about that.
No
Anyway, I want to introduce Musa, who's a geoscientist at ExxonMobil. And he'll be talking to us about sparse pseudo-sources in volcanic stressing. Let me just tell you a little bit about his career. He's alumni of Stanford's Exploration Project, where he conducted research in seismology, geomechanics, multiphysics, modeling, and subsurface property estimation. He has experience in industry and academic R&D on topics in statistical and machine learning, inversion, optimization, and as well as scientific software development in applied mathematics, engineering, geosciences, remote sensing, and data analytics. He's completed numerous projects, taking them from concept to real-world application. And without further ado, I'm going to go ahead and cede the screen to Musa and let him get us started.
Thank you, John. Thank you for the invitation and for your introduction. Good afternoon, ladies and gentlemen. It's my pleasure to share some interesting problems that I've encountered in theoretical geophysics with you today. What I'm going to talk about has almost nothing to do with petroleum geosciences. Actually, this is more about volcanology and study of magmatic processes. However, as you'll find out, the mathematics behind these processes is sort of universal and is applicable in many situations. So some applications outside of volcanology are also possible. Okay, the reason why I talk about this is to make sure there is absolutely no conflict of interest. Obviously, at ExxonMobil, I worked on a number of topics that intersected with my work at SEP at Stanford. But at Stanford, in addition to the usual petroleum geoscience, I also dabbled at a lot of other things. And some of them actually turned into a fully fledged career that I'm studying now on the West Coast as a computational scientist working in tech. And again, without further delay, so let me start talking about this topic. So sparse pseudo-sources of volcanic stressing. So why sparse pseudo-sources and why pseudo-sources? Okay, so basically, I know everybody is busy, so in the interest of time, I always kind of include a summary of my talk upfront. So as I said, this is not an oil and gas work, but this work does have numerous applications outside of volcanology. It has applications in hydrogeology, environmental engineering, and also carbon sequestration. So the ultimate objective of this study is to help with understanding magmatic processes via measurements of deformation. Okay. So everybody knows that changes in the subsurface, such as magma flows, changes in pressure changes inside magma chambers may result in deformation. Some of that deformation can be measured on the surface, and being able to make any predictions on with regard to the state of the magmatic processes from those measurements is extremely important. About that later. So some existing approaches to modeling deformation due to a pressurized cavity. So basically, we can think of magma chambers as pressurized cavities. Those existing approaches are either approximate or computationally very challenging. For example, they involve applying such methods as finite elements. And inversion is almost always semi-empirical. By inversion, what I mean by inversion is trying to figure out the geometry and, if possible, volume, the geometric extent, if you will, of the magma chamber solely from surface observations. So those methods are still very empirical, very much empirical. So the new approach that I'm going to talk about today is, I believe it leads to a very fast and, according to the experiments I've run so far, very accurate numerical modeling of deformation that is regardless of the complexity of chamber geometries. In other words, unlike finite elements, where the application very much depends on the geometry, because we have to come up with some kind of tessellation and non-uniform grid to make it work for complex geometries. Here, we try to take this one factor, the complex geometry, out of the equation. I'll show how. Still, I have this, red cross here, red dagger, basically, because it's still work in progress. I don't know exactly what are the limitations of this approach. So I don't know where, if ever, when, if ever, it will break, actually. So maybe, who knows, one of you will be interested in this problem and, will help me find out. Now, another important thing is that this method that I'm presenting today, basically, it opens a few interesting avenues for a quantitative inversion of chamber geometries. Okay, so in other words, the current trial and error, semi-empirical methods of figuring out the geometry of magma chambers and geometry of calderas and so on and so forth may hopefully be replaced with something a bit more automatic. Okay, now so that you know what we're going to do, first I'll explain why this problem matters. A couple of words about the existing approaches. Then we'll talk a little bit about the so-called unconventional reparameterization as a way of reducing an intractable computational problem to a tractable one. And then we basically move on to this equivalence of pseudo-sources and pressurized cavities. Okay, so that is basically the gist of this methodology. We will not limit ourselves to geophysics here. So we'll talk about the actual machinery of how I solve this problem using large-scale mathematical optimization with sparse priors. And also, discuss some tentative initial steps for tackling the inverse problem of resolving chamber geometries from surface deformations. Okay, conceptual model. I borrowed this slide from the USGS website about magma chambers. So obviously we're all geophysicists or geoscientists, so we know what a magma chamber is, but just a sort of high level overview for everybody's benefit. So basically we're talking about magma chambers that are not limited to something like this ellipsoidal magma chamber. Realistic magma chambers could be, anything from, penny-shaped, oblate, to even almost spherical to, oblique. And of course, all magma chambers have dikes and sills with them, and those dikes and sills also have their contribution to the subsidence or uplift. Okay, so and that's what makes this problem actually of trying to understand what this magma chamber, magma filled cavities inside the earth look like, very challenging, because in reality this body, this network of magma filled cavities could be extremely irregular, tree-like, and in some places could actually be in contact with fault lines, and also effectively turn those fault lines into magma conduits and so on and so forth. Now, pressure change in the magma chamber, and also dikes and sills, just for the benefit of those who never did any kind of volcanology course, I can actually quickly show what is a dike versus a sill. So basically, this vertical conduit, it looks very much like a dike. Something vertical is a dike. Something that looks like a basically windowsill, that's a sill. Okay, so those would be horizontal. They're not shown here on this picture. Now, another important thing about volcanic deformation is that magma-induced or pressure-induced deformation is often accompanied by faulting. It's this famous ring faults, for example, okay, around Kilauea is a well-known effect, basically. So maybe, again, I will annotate this, okay? Just if you give me 1 second, right, then I will be able, to do that. Yeah, annotation is not allowed. Okay, so no problem. So annotation is probably not allowed in your meeting, but that's fine. Okay, so faulting, usually normal or maybe reverse type of faulting, circular faults that are around the volcano associated with some sort of subsidence when magma is released, the pressure drops, and pressure drop increases stress, and so the stress is relieved by faulting along those normal or reverse faults. This mechanism is not completely understood, by the way, but again, the point of this is to basically show that it's an extremely important problem from hazard identification point of view, and also in the opposite way, sort of kind of assessing the explosive potential, for example, assessing the risk associated with events like what happened in the 1980s in Washington State. Okay, so enough talking about this conceptual model. Now let's talk math. All right. So how can we formalize this problem of, for now, forward modeling, okay, surface deformation from pressure increase or pressure change, uniform pressure change in this case, inside a chamber. Here we have this sort of simplified but surprisingly, powerful model. It's been applied to practically every volcano. So it's a spherical chamber, And this red vectors, they are normal vectors, and they denote the effect of pressure. So basically, what I'm trying to say here is that the normal stress, the normal traction associated with this pressurized cavity is equal to the pressure. Okay, this is the second boundary condition that I've written here. Please note that I use negative stress notation. I'm assuming that positive stress is tensile, and so compressive stress is negative. Okay, so compressive is negative. It doesn't really matter. It's just a convention. Another thing that you see here is that summation is carried out on repeating indices, but only if one is covariant and the other contravariant. I'm a mathematician. I don't like summing on indices that are at the same level. Okay, and the fact that there is an index which is both covariant and contravariant in N is not a problem. That means one of them was pulled down. So this is the mathematically correct way of saying that the normal traction is equal to pressure. Okay, what about that equation at the top? This equation at the top is, you can recognize, this is an elastostatic equation with a little bit extra, actually. So we have some body forces, and we'll also have this distributed dilatational centers of dilatational pressure forces. Okay, now that pressure and this pressure are different things. Okay, but there's a reason why I left this thing here. I'll explain it in a moment. Okay, so in addition to this pressure boundary condition on the chamber walls, we also need to impose some sort of boundary condition on the surface. And typically that's a free surface boundary condition, which means that the normal component of attraction is equal to 0. Okay, and indeed, well, above the surface is just air. And of course, there's not much tension here, of course. That's why we impose this boundary condition. All right, so free surface boundary condition is normal stress equals pressure plus the elastostatic system. That's it. So that's what we need. We basically need to solve in order to basically solve the problem of forward modeling the effect of pressurized cavity on deformation. Of course, here I'm assuming that in this equation, I'm assuming that the medium is homogeneous. It's again in volcanic applications and even in applications to earthquake deformation, this is a surprisingly, acceptable, assumption. However, of course, there is nothing prevents us from reformulating it for a heterogeneous, for example, for layered medium. Okay, so what's the problem? So why is it so difficult to solve this problem? Now, as you know, if we have Green's function either analytically or maybe pre-computed in some kind of tabulated form, or maybe Green's function that can be applied, numerically on the fly. Now, such methods exist as well. Then finding a numerical solution to this problem should be fairly straightforward. It would be some sort of convolution, or in this case, actually a sort of a version of a non-stationary convolution with that Green's function. Unfortunately, Green's function, that is Green's elastostatic tensor for half space minus such an inclusion, even the simplest one, such as a spherical inclusion, is unknown. That's a big problem, actually. As a matter of fact, that problem hasn't been solved yet. And the closest that people came to solving the problem of finding Green's function people always use, articles with Green's function, and I think it's kind of atrocious, isn't it? So, the closest that people, got to finding Green's function for this particular problem, that is half plane with a spherical inclusion, was a solution, asymptotic solution by McTighe. So basically what he did, he sort of did a series of approximations where first he would construct an analytical solution in a full space. It's easy to construct, it's very straightforward. Because such an analytical solution wouldn't satisfy boundary conditions on the free surface. They would have to, so kind of compensate for them by using the mirror image, approach. Again, a standard approach. It's standard approach that works in many cases, but not for multiple connected domains. And this is a multiple connected domain. So once you fix your boundary conditions on the free surface, the boundary conditions on the sphere walls get violated, then you have to correct those, and so on and so forth. In the end, you get a series, asymptotic series, that converges under certain assumptions. However, it's not an analytical solution. Okay, now, what is the most kind of general and so widespread, widely adopted approach to solving this problem? I'll talk about that later. So it's finite elements. Okay, well, here's an example from my former professor, Paul Siegel. It's a 2020 work. It's a relatively simple cavity, sort of elliptical. And here, finite elements are used to basically forward model the effect of pressure and also a slip on a fault. And you can see that in the neighborhood of the fault and also of the ellipsoidal, actually, in this case, a 3D cavity. We have mesh refinement. So computationally, it's non-trivial. This problem is non-trivial, and even the first step of building the mesh is actually could be quite challenging. So how can we simplify this problem? Is there a way for us to cheat, kind of use something like McTighe's method, but something that would work for a wide variety of inclusions of chambers? Intuitively, that should be done. The only reason that McTighe and before him Eshelby and after him Yang used some sort of asymptotic approximation was that the spherical inclusion, the cavity, was relatively simple, either spherical or elliptic, ellipsoidal. But if we remove this constraint of having to be analytical, looking for an analytical solution, and think of, some sort of numerical approach that is conceptually similar to this asymptotic, approach or analytical approach, we should be able, at least intuitively, it sounds not unreasonable, but we should be able to come up with some kind of technique. Okay, and that's basically what I'm proposing here. Okay, so the basic idea is a bit like the method of images. It's a bit like, in some sense, philosophically, very similar to the techniques that our buddies at Center for Atmospheric Research, CAR, applied to the Boussinesq equation. It's quite similar also in some sense to McTighe's approach. So what we're trying to do, the basic idea is to use the half plane, that is half space Green's tensor, the one that we do know. In other words, it's a Green's tensor for for the half space with the free surface boundary condition on the surface, but no inclusion. Okay. Solutions, such Green's functions are known. In 2D, it's a well-known Millin's function, and in 3D, it's a Midland's frightening 2 pages long solution, the exact analytical solution, but they are known. So use them, but how? We cannot simply take them and use them in the formula for, for forward modeling the displacements. Such a formula is only correct if we use the correct boundary condition, correct Green's tensor with the corresponding boundary conditions. That is, Millin's function will have to can only handle boundary conditions along the boundary, okay, and also take into account some distributed forces, whatever. But it will not be able to handle the boundary condition along the surface of this sphere. But we can cheat. We will try to sort of continue our solution domain inside the chamber. And we will, and because we don't care what's inside the chamber, that's not part of our, our domain. Okay, it's not part of our problem. We have complete freedom of doing whatever we want there. We will populate the inside of this spherical chamber with pseudo-sources, and we'll make those pseudo-sources such that if we forward model the formation from those pseudo-sources, the stress upon the boundary of this cavity will be equal to our boundary condition. In other words, we match our boundary condition by somehow artificially extending our solution beyond the boundaries. It's a bit like a method of images. So essentially, it is similar to that, except I propose to do that numerically. Okay, how? Now, it's a very well-known fact that it is possible to approximate uniform pressure on the walls of a spherical cavity in a full space by some triaxial sources inside the chamber. That's a well-known result by Eshelby. And there are interesting, extensions to that result, later extensions. It's also possible to use, centers of dilatation along the line and so on and so forth. But what's important is that this problem is fundamentally non-unique. There is a lot of freedom to what we can do inside the chamber. And so if we want to solve this problem of somehow cheating and matching our boundary conditions by introducing these non-physical functions, sources inside the chamber, we need to constrain it somehow. And I suggest constraining it using sparsity. I'll explain in a moment why sparsity. So here's what we do. Now, there's no need for us to remember any of the previous equations. Now, you can think of this as just a fairly, typical problem of maybe sparse coding. In this case, is actually sparsity promoted inversion, sparsity promoted optimization. Okay, so basically we have this term, which is you can think of it as a prior It's a Laplace prior, basically, that tells us that this B being some operator and U being, for example, the moments distributed inside our domain, must be sparse. L1 means sparsity. In this particular case, in my experiments that I'll show you in a moment, B is the identity matrix. So basically, it's just I want the pseudo-sources to be sparse. I want to have as few of them as possible distributed somewhere inside this chamber, and such that they predict the pressure upon the barrier. So they produce exactly the same effect as if the cavity was filled with magma. Now, the second term is simply the forward modeling operator for the normal stress, and our data is the actual boundary condition, is the pressure. So if I may go back for a second, so basically this equation, this last equation, the third one, is what is inside that two law. Okay. Now we formulated this problem of faking our boundary conditions as an optimization problem. Of course, it's a very large optimization problem. Actually, specifically for this seminar, after I tried my algorithm that uses basically a method for very large optimization problems, I tried to see if something simpler could work as well, and try to use like a standard ADMM with exact quadratic solver. And my big and powerful server actually ran out of memory. Okay, so what we're going to do a bit later, after a couple of minutes, after I share some of the experiments with you, I'll tell you how we can actually solve this kind of problem. Okay, now let's imagine we have the software and some suitable mathematical optimization method that can solve this problem for very large vectors U. And for the operator A, which is basically an extremely ill-conditioned operator, we'll see that in a moment. And on top of that, this optimization problem has a non-smooth objective function, so the L1 null. Okay, so let's assume we can do that. What can we get? All right. First of all, how can I impose this sparsity? I'm assuming that all those are actually imposing this condition that all the moments should be inside some subdomain of the ellipsoidal cavity. Okay, here this gray area basically. Okay, and I solve the previous problem there. And let me show you some results for this, for now, simple spherical chamber. Remember, even the spherical chamber does not have a good analytical solution, only asymptotic, and which could be very wrong in a near field, even in a near field. Okay, so this is what I get in terms of vertical displacement. All right, so basically it tells me that things are pushed up. Well, that's not surprising, of course. You see this sort of eclipse in the middle. That's a standard way of sort of kind of eclipsing, occluding the very large values that are inside this chamber. Remember, inside the chamber, there is no physics. Inside the chamber, pseudo-sources. Okay, so we're not really interested in seeing them. Okay, outside is that's what we're interested in. Okay, now this is what we get in terms of horizontal displacement. Interesting. So basically, it tells us that on the right side things are moving right, and left they're moving left. Well, not surprising, of course. And this is what the actual displacement vectors on the surface look like. So maybe first I'll show you this. Okay, so the red curve is the vertical displacement, and the blue one is the horizontal displacement. Horizontal displacement is negative on the left side of the inclusion. Well, obviously, because things are moving left, and positive on the right side because things are moving right. And we have an uplift. Well, nothing surprising, obviously, but the most important thing is this. Now look at this. Because this is half space, and this inclusion is relatively shallow, it's only like 250 meters deep. There's this area of very rapid change between the boundary of the cavity and the surface. That is the most challenging, thing basically about solving this problem. Analytical or asymptotic solutions are simply unable, at least for relatively shallow cavities, to quickly take into account this need to, sort of change from radial orientation to something quite different, dramatically different. But our solution apparently does. In fact, I can tell you that the stress misfit was about 1% of the original, but it was not zero. That's important to say, that I did not get a zero. So there's still some error in terms of fitting the boundary conditions. And I don't know if there may be cases where this error may become more significant. Okay, so I need more experiments. Now, this is just a spherical condition, inclusion. What about something a bit more interesting, like penny-shaped elliptical? Okay. Again, if we had to apply something like finite elements, this change would entail a significant reworking of everything we do. In fact, would have to introduce some sort of a new mesh. Design will have to be different. The refinement will have to be different. So everything would have to be different. Okay, this methodology simply does not care. We only need to have a parametric representation of the surface, and we need to have parametric representation of all the normals. That's also important. So the two things are necessary, and that's it, nothing else. In this case, the mask is again a similar a smaller elliptical enclosure. And here's what we get in terms of vertical displacement. It's kind of similar to what we had with the circular, but again, let's take a close look at the displacement vector field. We see that in fact, I have a numerical confirmation that somewhere near the boundaries there was some deviation from the normal stress field. Okay, so along those boundaries, deviations were reaching about 10%, something like that. But overall, again, the misfit was reduced to approximately, to actually less than 1% of the original one. It's important to note that regularization actually may be hurting us at this point, So, yep, there's a question. All right. 3:40, maybe another 10 minutes of presentation to allow for questions. Absolutely, yes. Actually, I think I'll be done in about, slightly more than 5 minutes. Okay. All right. Okay. But more important is this. The actual displacements. The vertical and horizontal displacement curves. Now, perhaps you remember that in the previous case, our maximum displacement was about 1 centimeter. Here, maximum vertical displacement is 15 centimeters. So what happens here, just makes sense, obviously, is that we have a much wider surface pushing up. Okay, and a smaller one pushing sideways. So it's edge on, the inclusion is edge on its side. And so this result makes sense. And the last one, this is probably the most useful from the standpoint of applications. So it's about 45-degree tilt, elliptical, ellipsoidal inclusion. So again, the algorithm just works out to the box in this case as well. And no need for any customization, just the normals and the parametric representation of the curve. Okay, and again, this case is much more challenging because here we have a very sort of extreme case of stress heterogeneity, basically. And nevertheless, we again match the boundary conditions. The misfits in this case were against actually significantly less than 1% than the original one. And if we look at the surface displacement, it's less than 1 centimeter, not surprisingly, because much of the inclusion is under the surface. Now, this is all well, but in order to be able to solve this problem, we again need to have some way of tackling very efficiently very large scale regularized optimization problems like this. Obviously, this is not a math talk, although I'm a mathematician. I'm more than happy to discuss details of this algorithm and its implementation with you. Just let me give you a very high, level overview. So the approach that I take here differs from existing approaches in that prevalent existing approaches in that in existing approaches, basically what they try to do, if they apply something like ADMM, for example, some kind of splitting method, they solve some intermediate smooth differentiable optimization problems approximately, okay? And then in some external loop, they basically repeat the process over and over again. Because of that, it is extremely, in typical problems, geophysical problems, for example, problems of seismology, full wave inversion, application of things like ADMM is highly inefficient. However, what I do here is basically a sort of developed a trick for figuring out how to, sort of continuously solve the smooth optimization problems that arise in ADMM without having to restart them. Okay, and this methodology is applicable to other problems. Well, here's an example that I wanted to share with you. This problem doesn't really need a very powerful solver, to be honest, but still it is ill-conditioned. It is an extremely noisy, image. So you see an image of an old Soviet car and Baku, my native town, on a winter day. So I added a lot of noise, 90% random Gaussian noise. Just take a look. It's 90% of the maximum magnitude. That's what I mean by 90%, by the way. There are different definitions. And here, the same algorithm that I applied to that geophysical problem, I applied here to this denoising problem. We lose some details, of course, because it's, blocking is promoting optimization now, but nevertheless, we've recovered a lot of information. Of course, we can go carry on and refine some kind of coarse details and even use it in some geophysical, statistical learning context. Obviously, that's basically what happens here. We sort of extract the essence of a car, anthropomorphic object, and anthropogenic, object, and also extract the essence of a cityscape. Now, this is I developed this technique for geophysical applications. And you may say, so why use them outside of geophysics if good alternatives exist? Well, just take a look at this curve here. It's an incredibly ill-conditioned problem. This is condition number. And it's also a very large problem. So we're talking about basically million-dimensional problem. And this same algorithm that I described to you here and we apply to the magma chamber problem was applied to this ill-conditioned problem, the TV regularization. Now, alternatives are so basically just carry on this restarted conjugate gradients, algorithms that are basically based on the direct application of conjugate gradients with some sort of splitting technique like Vista, ISTA, and so on and so forth. They basically trudge on while our approach, because it takes advantage of so it works across the iterations of ADMM. It converges much faster. Again, that was just a way to sort of maybe interest some of you in trying this, and especially in the context of applying them to this problem of studying magma chambers. Right, that's it. I'm done. I think we have time for questions. I'd be more than happy to entertain any questions and also hear your comments and suggestions.
Thank you very much, Musa. I will open the floor to questions.
Hey, geophysics questions, mathematics, coding, whatever you want, no problem.
Can I ask one?
Absolutely, yes.
Well, Musa, thank you very much. That was awesome. I got to tell you, you should do radio. Your voice is just really fun to listen to. It was really captivating, this presentation. I appreciate that. Also, volcanism is very interesting. When I was a kid, Mount St. Helens erupted.
Yeah.
Like an ash. Now, what's very interesting to me, my understanding is part of the failure there was an assumption of homogeneity, or at least a failure to know about certain failure planes and so forth. Could you comment further on your assumption of homogeneity and when it can be appropriate to use that?
Okay. So, yeah, that's a very good question, actually. So there are two different things here, actually. So one is the homogeneity of the medium in the sense of homogeneity of its parameters. So the shear modulus, the Poisson ratio. Okay, so it's one thing. Another thing is sort of a different thing, actually, at a macroscopic level, is presence or absence of faults, okay, that can be activated because of change of stress regime. Okay, so it's not really necessary to introduce heterogeneous elastic parameters to actually kind of take into account, to introduce those faults in the medium. Those faults can be, basically introduced separately as, separate source terms in the corresponding, Green's tensor formula. Okay, so that's the good news. So the good news is that that kind of heterogeneity can be actually taken care of without changing, without having to introduce non-constant mu and nu. Okay. A good example of that work is actually one recent work on a couple of actually recent works at Stanford on Kilauea. So basically, what happened there is there was this subsidence associated with a significant eruption event, and that subsidence actually was accompanied with a faulting along a ring fault, basically, that sort of spirals around the volcano. And to model that, there is no need to sort of introduce heterogeneous shear and other coefficients, Lemay or Poisson ratio. So basically, those papers basically used constant values. They just modeled those faults based on a friction stick-slip basically mechanism. And the slips on those faults were triggered when the shear component of the stress exceeded friction coefficient times the normal component of the stress. And so when that happened, they were modeled as, slips on those faults were modeled as sources, basically as sources in the Volterra formula, in this formula for the solution. Thank you, Michael. That's a very cool question. But still, you're right. There are situations where you want to have, we want to have heterogeneity, and in many cases, a layered medium is a good approximation in the volcanic cases. And then instead of Volterra's formula, we have to use something like, matrix methods, for example, or something like I and Professor Zobak used in 2018, basically sort of hybrid matrix Fourier method that basically requires solving a simultaneous system of ordinary differential equations. But anyway, there's no need to go into those details, but there are ways to handle that.
Okay, thank you. So I'm going to see if there's another question here, but I'm going to leave Musa, I'm going to leave Leah here to be in charge because I'm going to have to sneak out here in a minute to go open the Zoom session for the faculty meeting. But let's see if we have any other. I actually have a question, but I don't know if I have time to ask it. But let's see if there's another question from the audience. Well, maybe we'll just go ahead and wrap up then. And rather than asking a question, I think I'll just make a comment. You seem to imply at the beginning that this kind of problem didn't have that much application in oil and gas. You did mention some things after that, but I would say there's a lot of application of this kind of methodology, not just for when you have faults and things, but the idea of reservoir deformation and being able to map. I noticed in your I think in your bio or something you mentioned some tiltmeter applications, and those are very interesting for reservoir deformation and hydraulic fracturing, I think. So thank you for a very interesting talk, and we hope to see you. There you go.
Actually, I wanted to share something else. You're absolutely right. And I kind of mentioned that, but those applications are, they're more along the line of these pore pressure effects. So
right.
Pore elastostatic applications. Yeah, absolutely. I totally agree. Those are very important. And those are actually easier, believe it or not, than fluid-filled chambers. And sometimes people use this, wrong physics, basically. There's pore elastostatic models to describe fluid effects or pressurized chambers. Again, the thing is, yes, in oil and gas, there's pore elastostatic models are extremely important. Yes, absolutely, they are pore elastostatic and pore elastodynamic. But what I wanted to say was that this problem is kind of fundamentally different. I'm not saying that it doesn't have applications. Yes, in carbon sequestrations, actually, there are some models where this magmatic chambers basically can be applied. And also some examples in pressure injection, steam injection in sands, in oil sands. It's also some potential for application there, but to be honest, but they are relatively few, to be honest. Anyway.
Okay, great. Well, and I'm find this kind of modeling and inverse applications are very interesting, I think. So, okay, well, I hope your power returns to you soon. And we really thank you for your time spending the afternoon with us. So thanks again, Musa, and good luck with the weather repairs.
Oh yeah, yes. Thank you very much. Thank you, John. Thank you, Michael. Thank you, Leah. Thank you, everybody. And well, I'm sure we'll catch up sometime in the future.